Alright, in this video I'm going to go over section 9.6, which is all about alternating series and this thing called absolute convergence. So I'm just going to do a bunch of examples, one to show you how to do the alternating series test, and then a couple other ones on how to show something is either conditionally convergent or absolutely convergent. Alright, so first off, let's look at one from the worksheet. This is number 1C on worksheet 9.6. Which is the series k equals 2 to infinity of negative 1 to the k, ln of k over k. So here, this is definitely an alternating series. You can tell what an alternating series is if it has like this negative 1 to the k in it. So the first couple terms of this series, right, if I would list this out, would be positive ln of 2 over 2 plus a negative ln of 3 over 3. Plus a positive ln of 4 over 4 minus ln of 5 over 5. All right, so it goes plus minus plus minus. That's an alternating series. So if I want to prove that this thing is convergent, I can use the alternating series test. First off, I could try to do the divergence test. That always applies. So if I look at the limit as k goes to infinity of negative 1 to the k, right, ln of k over k, for an alternating series, this can be a little bit weird, but you can separate this ln of 1 to the k out. So I can do the limit as k goes to infinity of negative 1 to the k. And I know that that's not going to really approach anything. That's just going to be the plus minus that flops back and forth. But I can also do the limit as k goes to infinity of ln of k over k. Right, so I can do the multiplication of these two. So I'm applying the limit to this, and then I'm applying the limit to that. That's one of the limit laws, and that's completely fine. So I know that this limit here doesn't really exist, it's just the plus and minus sign. Here I would get infinity over infinity, but if I use L'Hopital's rule, we see that this is the same as 1 over k over 1, correct? Because the derivative of ln of k is 1 over k. And so here I get 0, so this thing goes to 0. So essentially what I have is the limit as k goes to infinity, right, of the negative 1 to the k times 0, which is just going to be 0. So this thing's going to flip-flop back and forth, but in general the terms are going towards 0, negative 0, plus 0, right? It all goes to 0. So here this is inconclusive. Okay, so if I go back to my series, I want to do the alternating series test. And here, what this test does is it kind of ignores that negative 1 to the k, and this is what's called the a sub k plus, a sub k. So those are the magnitude of the terms. So it says, first part, we must show, right, that it's decreasing. That, right, a sub k plus 1 is smaller than a sub k. Now this is a little bit more difficult to show, right? So is ln of k plus 1 over k plus 1, right, question mark, is that less than or equal to ln of k over k? Well, sometimes this can be difficult, so I like to just show that, right, define a function, ln of x over x, that's identical to the term, and show that the derivative is negative. So here, f prime using the the quotient rule would be right, x times 1 over x minus, let's see, ln of x. So f prime of x would equal 1 minus ln of x over x squared. And we can see here, right, this thing is always positive. The bottom is always positive. And the top, so we can say, right, f prime of x, right, is less than 0 when 1 minus ln of x is less than 0, which means ln of x must be greater than 1, which means x is greater than e. So even though this series starts at 2, right, a sub k equaling ln of k over k is decreasing for k greater than or equal to 3, which is fine. So in that first term, it might increase or decrease, right? But after 3, it's definitely decreasing. So that part checks out. Now, secondly, this limit has to be 0. So the limit as k goes to infinity of ln of k over k, right, is that 0? Well, we already did that up there in the divergence test. I'll use L'Hopital's rule. And yes, that is 0. So that checks out. So these two things are satisfied, which means the original series converges. the alternating series test. Okay, so that's how we use the alternating series test. This part's a little bit hard because it has a transcendental term, but I always resort to finding the derivative. Okay, so let's look at another one. So here, a series is conditionally convergent if it converges itself, but then the absolute values of its terms do not converge. So anytime when you're using when you're looking at an alternating series, you could just jump right into the alternating series test, but you won't prove absolute convergence if you do that. So a lot of times it's best to just hit this thing with an absolute value. So here I'm going to check for absolute convergence. So I'm going to ask, right, is this thing absolutely convergent? And the reason we kind of check that first is because we already have all these tests, right, ratio test, root test, whatever, that apply to series with positive terms. So I can use all of the tests that I have before, right, to test absolute convergence. Okay, so if you do the divergence test here, it'll be inconclusive. So I want to point that out. So let's look at absolute convergence. So here I'm going to look at not the original series, I'm going to look at the absolute value of the series. That's what absolute convergence means. So when I do the absolute value of this, k is always positive, so that just stays the same. 4 to the k also always positive. The only thing that gets deleted here is the 1 to the k. So this is the series now that I'm looking at. Okay, since it has a, let's see, a 4 to the k, and I'm going to use the ratio test for this. So the limit as k goes to infinity of, let's see, k plus 1 over 4 to the k plus 1 times 4 to the k over k. So I get the limit as k goes to infinity. There'd be a 4 left over on the bottom. Up top I have a k plus 1, and there's also going to be a k in the bottom. So here I have the limit as k goes to infinity. Notice that this is infinity over infinity, so I'll do L'Hopital's rule. And I would get 1 over 4, which is 1 over 4, and that ratio is less than 1. So since r is 4, which is less than 1, this series is convergent. Now, if the absolute value of the series is convergent, that means the original is absolutely convergent. And I don't even have to check for conditionally convergent. Okay? So that's how you show something is absolutely convergent. You just delete that negative 1 in the k and try it out. Here's another one. So let's check this one out. So here the k is in the exponent. So I'm just going to play with this thing a little bit, and we'll see that this is a geometric series. So this is negative 1 to the k. E to the negative k is the same as over e to the k. So I can rewrite that as k equals 1 to infinity. So here both things are being raised to the k power. So what is my ratio inside? Well, it's negative 1 over e. So we already know that this is a geometric series, right, with r, the absolute value of r being the absolute value of 1 over e, which is 1 over e, which is less than 1. So this is convergent. So this thing is at least, the original is at least conditionally convergent. So let's look at absolutely convergent. Again, I would just take this thing, k equals 1 to infinity. I would do the absolute value. And I'm just left with the series k equals 1 to infinity of e to the negative k. And we know that this can also, like we just did, be written as 1 over e to the k. And so I can write this series as 1 over e all to the k. And again, this is a geometric series, with r, absolute value of r, actually just being 1 over e, which is 1 over e, which is less than 1. So this is convergent, which means the original series is absolutely convergent, which is kind of obvious. In fact, I can go back to this point right here, and while I'm here, why don't I just do it? I can actually find what this thing is convergent to. So if I switch the bounds, this would be from 0 to infinity of negative 1 to the e to the j, where I've already pulled out the extra negative 1 over e. So I get negative 1 over e over 1 minus So it'd be plus 1 over e. So this is negative 1 over e times, let's see, e over e plus 1. So I get negative e over e plus 1. So not only is this thing absolute convergent, but it converges to negative e over e plus 1. Okay. Let's try another one. So how about this one? Here is a here's another alternating series, because it has a negative thing being with a k in the top. So I could rewrite this as, if I want to pull out that negative 1 to the k, I can write this thing like this. All right, so that negative 1 to the k is there. It's just kind of harder to see in this case. Now again, the first test you should always do, right, is the divergence test. Now I could just start doing the ratio test here or something else, right, to the absolute value, trying to look for absolute convergence, but always do the divergence test first. And so I want to do the limit as k goes to infinity of negative 1 to the k, 2 to the k, over 1 plus 2 to the k. Okay, so again, for an alternating series, just get that, that negative 1 to the k out when I'm doing this limit. And just keep in mind that this thing is going to flip-flop. So right now, if I'm left with this thing, it would be divergent, because this limit doesn't exist. However, if this thing that's left over, right, as we saw before, if this leftover thing doesn't go to 0, then we're going to have trouble. So what do I get here? Well, in the top I have a dominating of 2 to the k. In the bottom I also have 2 to the k. So I'm going to divide everything by that. So if I divide everything by 2 to the k, I would get this. 1 over 1 over 2 to the k plus 1. So as k goes to infinity, right, we see this little term right here goes to 0. And so I would be left with the limit as k goes to infinity of negative 1 to the k. And this limit here is equal to 1. So essentially what I have here is, right, the limit is oscillating between negative 1 and 1. Right? So it doesn't exist. And doesn't exist doesn't equal 0. So this thing diverges by the divergence test. Okay? So that test is always available, and we always have to remember that. Now, up until now, I would say those are kind of easy examples. So this one here is going to turn out to be a little tricky. So this one is going to be conditionally convergent. So first, if you look at the divergence test, it's going to be inconclusive. Here's why. The negative 1 to the k, right, flip-flopping all the time. However, the top thing I have the square root of k, and the bottom I have a higher degree of k, correct? So the bottom dominates, and so this thing will go to 0. But first, I'm going to check for absolutely convergence. Absolutely convergent, question mark. Okay, so that means I got to test the series k equals 1 to infinity of the square root of k over 3 to the k minus 1. All right, so I just deleted the negative 1 to the k. Now, looking at this thing, the terms definitely go to 0, but that doesn't mean it's convergent. I have a 3k minus 1 in the bottom. I would say I'm going to use the comparison test here. So if I just delete this minus 1, I could show that this thing is definitely greater, right, than root k over 3 to the k. Right? Simply because I'm subtracting off 1, so this has a smaller denominator, which means it's a bigger number in general. Correct? So how does this thing reduce? Well, I have k equals 1 to infinity. The root k's would cancel. I can bring the 1/3 out, and this would be 1 over k to the 1/2. So if I'm looking at this thing is a divergent p-series, because p is 1/2, which is less than 1. But this thing is bigger, I'm sorry, this thing is smaller, right, than this. So by comparison, this diverges. So this series, the original series, is not absolutely convergent. Now, that doesn't mean that the original series is not convergent, right? So this thing could still be convergent, which would mean, since it's not absolutely convergent, that it's conditionally convergent. So the only way I can test this now is using the alternating series test. So here, define a sub k to be this thing. Two things have to occur, right? Is the next term smaller than the previous? Okay. Well, so again, sometimes this can be hard to figure out. So I'm going to call this function this, and then what would be the derivative? Well, the derivative would be the bottom squared, so the bottom times the derivative of the top, so that's 1 over 2 root x, minus the top times the derivative of the bottom, which is 3. So f prime of x, right, is 3x minus 1 over 2 root x minus 3 root x all over 3x minus 1 squared. So again, look at the top thing. The bottom is always positive, so whenever the top is negative, that is when it's decreasing. So I have 3x minus 1. So I can say f prime of x is less than 0 if 3x minus 1 over 2 root x minus 3 root x is less than 0. So solve this thing for x. So I have 3x minus 1 over 2 root x must be less than 3 root x. We have multiply, so 3x minus 1 must be less than 6x. So let's see, negative 1 is less than 3x. So as long as x is greater than negative 1/3, which is true because look, k is always bigger than 1. Right? So a sub k plus 1 is less than or equal to a sub k for all k. Right, so the derivative, this is just saying the derivative is negative when x is bigger than negative 1/3. Now switch that back to k. K is always bigger than 1, so that thing is always going to be decreasing. The second part is the limit as k goes to infinity of root k over 3k minus 1. Does that equal 0? Well, here I get infinity over infinity. So why not use L'Hopital's rule? So we got this. So this is 1 over 2 root k over 3, which goes to 0. Therefore, this series is conditionally convergent. All right. So I hope those couple examples helped. And that's all for today.